Last part of section 13.6 with two elements that we're going to visit now. First, a theorem that I mentioned several times up to now in previous parts. If f is differentiable at a point, and if del f is not the vector 0, then del f is normal to the level curve through the point. Let's look at an example. Find the vector perpendicular to the level curve corresponding to c equals 0 for the function f of xy equals y minus sin x at 0, 0. This is what the function looks like, the surface in 3D, and if we focus on the level curve c equals 0, here it is. What it is really is, if we look at it from above, it's really just y equals sin x, right? Because if this is equal to 0, 0 equals y minus sin x, therefore y equals sin x. So this question, it's possible to solve it with only 2 months of a first course of calculus. What we would do if we wanted to find a normal vector to y equals sin x in the plane is we would calculate the derivative, y prime equals cosine x, then we would figure out a vector that is tangent to the curve, and from a tangent vector we could find a normal vector. But we're going to do this problem using gradient, and it's really interesting because from what basically is a 2D problem, find a vector normal to y equals sin x, we're going to add a dimension to it to make it easier to solve. So we could easily create from y equals sin x a surface in 3 dimensions, which would be f of xy equals y minus sin x, and then focus on the level curve c equals 0. When we do that, we can calculate the gradient using partial derivatives. So del f equals negative cosine x times I plus 1 times j. And using the theorem above, we know that this vector, negative cosine x 1, is going to be perpendicular to the level curve that we have. At 0, 0 in particular, it means that the vector negative I plus j is perpendicular to y equals sin x. Notice how you can choose other points here. The vectors are all going to be a certain first component and 1 as a second component, so it appears that the magnitude of that perpendicular vector varies, and we know what it means. This magnitude doesn't have any meaning in the 2D problem, but it would talk about the slope of the tangent plane in 3D. Definitions for directional derivatives and gradient can be extended to functions of 3 or more variables. However, some interpretations, like the slope, aren't going to be appropriate anymore. If you think of the problem we saw in part 3 with the metal plate, we could now imagine a function that gives the temperature for a 3D object, maybe the engine of a car, and the temperature at any point in the engine. So we would have coordinates x, y, z, which are describing the position of the point in 3D, and the fourth coordinate, t, which would give the temperature. So if we're looking at where the temperature is increasing the fastest, it doesn't make any sense to talk about slope. But the idea is the same. So here's a simple example of finding a gradient with a function of 3 variables. Function f is given here, so the answer to A, we just calculate the partial derivatives. Fx is 2x, fy is 2y, fz is negative 4, and that's it. Find the direction of maximum increase of f at the point 2, negative 1, 1. We just plug in the values and we find the gradient at that point to be the vector 4, negative 2, negative 4. So that's it for this section. Congratulations, it was really difficult. There's 3 more exercises you should do, and that's it for now. Thank you.